So if we have a balanced chemical equation, we can use the mole concept and we can build a mass relationship for the chemical reaction. So for example, if you are given the mass of A, we can go from the mass of A to the moles of A by using the molecular weight of A. And then if you look at the balanced chemical equation, we can relate the moles of A to the moles of B. And after this, we can change the moles of B into grams of B by using the molecular weight of B. Let's have an example here. So this is a balanced chemical equation. So again, your chemical equation has to be balanced at first. Once you have a balanced chemical equation, you can express this equation in different ways. You can express it in a form of mole expression. Mole expression, this is why I said you need a balanced chemical equation, because these are your number of moles in here. So if I read it, I would say, okay, 2 moles of the hydrogen sulfide, these are reacted with the 3 moles of oxygen to form 2 moles of sulfur dioxide and 2 moles of water. This is the mole expression. Now, if you want to change it into a mass expression, we know that to go from moles to mass, you have to multiply by the molecular weight. So this is the molecular weight in here. So if I want to go from the moles to the mass of the H2S, I need to multiply by the molecular weight of H2S. The answer for these two is over here. So you're getting the mass in there. You multiply 3 times the molecular weight of oxygen, so it's 32. And then you multiply 2 times the molecular weight of sulfur dioxide and 2 times the molecular weight of water. And then you can get a mass relationship in the chemical equation. We can also change and express the chemical equation in the form of a molecular expression. Just remember that every mole corresponds to 6.023 times 10 to the 23 molecules, so I can relate the number of molecules as well. Please do not forget the coefficient in there. This is the balanced equation because this is very important to determine the number of molecules as well. So I cannot say for the SO2 I have 6.023 times 10 to the 23 molecules. No, it's 2 times 6.023 times 10 to the 23 molecules. So that coefficient contributes to also the number of molecules as well. Let's have an example. Calculate the mass of hydrogen sulfide that would need to react with excess oxygen. So it's telling me that I do have a reaction where I'm reacting H2S with oxygen in order to produce 115 grams of sulfur dioxide and water. Okay, let's add this water in there. So this is going to be my equation. Just make sure to balance the equation. Start with the sulfur. Make sure that the sulfur is balanced, and then go with the hydrogens and finally the oxygen. Balance everything there. And we're going to end up having, for every 2 moles of hydrogen sulfide, we're reacting it with 3 moles of oxygen. We're going to form 2 moles of sulfur dioxide and 2 moles of water. So what we are given is the mass of the sulfur dioxide. So this is what we need to start with. What we need is the mass of the hydrogen sulfide. You can see the relationship between them, that for every 2 moles of H2S, you are forming 2 moles of SO2. So I can start with the mass of the SO2. See, this is going to be my guide over here. So I'm starting with the mass of the SO2 because it is given. I will change the mass of SO2 into moles of SO2 because it needs to be still remaining SO2. I cannot jump to the H2S before changing into the moles of SO2, and then I can relate from this chemical equation between the moles of the SO2 and the moles of H2S. After I get the moles of the H2S, I can simply go to the mass of the H2S by using the molecular weight. So to build that, let's go ahead and start. We are starting with the given, which is 115 grams of SO2. Okay, now I want to change that into moles, right? So to change that into moles, I know that for every 1 mole of SO2, guys, the molecular weight, you would need the molecular weight for this problem for the SO2. So the molecular weight for the SO2 that is equal to 64.066 grams of SO2. This is grams per mole. Okay, grams of SO2 per mole. Okay, and then you would need the molecular weight of H2S as well, because every time you're going from moles to a mass, you would need the molecular weight. So you can calculate this, and it's going to be 34.082. This is a gram per mole of H2S. It's a grams per 1 mole of H2S. So I need the moles of the H2S, so the moles are going to be in the numerator. And the molecular weight is going to be 64.066 grams of SO2. So now I can go ahead and cancel the grams of the SO2 out. Once I am done from the moles of the SO2, I can relate this from the chemical equation in here, that I know for every, I need to cancel the moles of the SO2 and introduce the moles of the H2S, right? So I know that for every 2 moles of H2S, look at the chemical equation. So for every 2 moles of the H2S, I'm forming 2 moles of the SO2. So 2 moles of the SO2. Now it's not going to make a difference in there because the 2 and the 2 will cancel out. So now here I'm going to cancel the moles of the SO2 and the moles of the SO2. I will remain with the moles of the H2S. So I am here. Now I want to go ahead and change it into the mass. So to change it into the mass, I'm just going to go ahead and multiply. This is for every 1 mole of H2S, so that I can cancel this out. The molecular weight is 34.082 grams of H2S. This way, my answer is going to be in grams. This is 2 grams of H2S. This is an example of a reaction over here where I can show that you can easily see the mole concept in there and how we can have information about one substance, and we can relate it to another substance by simply using the chemical equation. Now the next example is similar, and this is number 34 in your homework. So this is how you solve it. It's exactly similar to the one above, same concept. So how many grams of nitrogen are required to completely react with 3.03 grams of hydrogen? So I'm reacting N2 plus H2, okay? So this one is going to be a combination reaction. N2 plus H2, and I'm going to form ammonia, okay? So I'm reacting into gas, hydrogen gas, and I'm forming ammonia liquid. You don't need to know, but normally ammonia is a liquid, but normally I would give you the physical state for each one of those. So balance your equation, please. And once you balance your equation, you're going to see that for every 3 moles of hydrogen, I am forming 1 mole, I'm reacting it with 1 mole of the nitrogen to form 2 moles of ammonia. So you need the mass of the nitrogen. This is what you need, right? So you need the mass of the nitrogen, and you are given the mass of the hydrogen. So start with the mass of the hydrogen, get the moles of the hydrogen, and from the moles of the hydrogen, you can relate that to the moles of the nitrogen. From the moles of the nitrogen, you can relate this to the grams of the nitrogen. So it's similar to the one above. I would need simply the molecular weight of nitrogen here in this case. The molecular weight of nitrogen is 28 grams per mole. This is the molecular weight of nitrogen. It's 28 grams per mole. So I'm starting with the mass of the hydrogen that is given. It's given that to be 3.03 grams of hydrogen. And I want to change this into moles of hydrogen, so I need to multiply it by the molecular weight of hydrogen. The molecular weight of hydrogen is 2, okay? So the molecular weight of hydrogen, that is equal to 2 grams per mole. Every hydrogen is 1, so that is going to be 2. So for every 1 mole of hydrogen, I have 2 grams of hydrogen. This is the molecular weight of hydrogen. So I am done with this. The grams and the grams, they cancel out. I introduced the moles of the hydrogen. Now I need to relate the moles of the hydrogen with the moles of the nitrogen. So I need to cancel the moles of the hydrogen, introduce the moles of the nitrogen. So I know that for every 3 moles of hydrogen, I am reacting it with 1 mole of nitrogen. So now I cancel the moles of the hydrogen, introduce the moles of the nitrogen, and now we're going to change from the moles of the nitrogen to the grams of the nitrogen. We're going to multiply by the molecular weight of nitrogen. So for every 28 grams of nitrogen, this is represented by 1 mole of nitrogen. So these units cancel out, and your answer is 14.0 grams of nitrogen. This is the same concept. I am given a chemical equation. Carbon monoxide reacts with oxygen to produce carbon dioxide. Balance your chemical equation. And the question says that how many grams of carbon dioxide form if 34 grams. So I'm given 34 grams of carbon monoxide. They are combined with excess oxygen. So I can start with the mass. I'm starting with the mass of the carbon monoxide. I am going to change the mass of the carbon monoxide into moles of carbon monoxide. And then I would need to relate the CO to the CO2. So relate the moles of the CO to the moles of the CO2 and get the mass of the CO2. What you need to form or what you need to find. So I'm starting with the given mass. The given mass is 34 grams of carbon monoxide. Carbon monoxide has a molecular weight of 28 grams per mole. So this is going to be 34.0 grams of CO. And we're going to multiply this by 1 mole of CO divided by 28 grams of CO. So this is going to introduce the moles of the CO. So we are here. And then I can relate the moles of the CO with the moles of the CO2 by looking at the chemical equation and seeing that for every 2 moles of CO, I am making 2 moles of carbon monoxide. So 2 moles of the CO2. I need the CO2 to be in the numerator, and I need the CO to be in the denominator so that I can cancel it out. 2 moles of CO, so I can cancel the CO out, and now I need to change the moles of the CO2 into the mass of CO2. That is 44 grams of CO2. This is the molecular weight divided by 1 mole of CO2, and the answer is 53.4 grams of CO2. Okay, number 4, in the reaction, methane and oxygen produces carbon monoxide and hydrogen. How many molecules? So now we are going with molecules. We are asking about molecules. We cannot pass by the molecules unless we find the moles, because we go normally from the mass to the moles to the atoms or molecules, right? So the moles are very important because the moles are going to give me a path in order to get to the molecules, and thereby using simply an Avogadro's number. So you can go from moles to atoms or moles to molecules. Here, this is a molecule. CO is not an atom; it is a molecule. So this is why I am using the molecule in there. And if I use molecules, then definitely I'm going to use Avogadro's number. Remember that for every 1 mole of CO, it contains 6.023 times 10 to the 23 molecules of CO. This is how you do the relation. So I'm starting with 1.6 grams of methane. This is 1.6 grams of methane. I am gonna, this is CH4. I am going to change this into moles of methane. So I'm going to divide by the molecular weight. 1 mole of CH4, that is divided by the molecular weight of CH4, which is 16 grams of CH4. So now I formed the moles of the CH4. We're going to change to the moles of the CO by doing a simple relationship between the carbon monoxide and the methane. So I know that for every 2 moles of carbon monoxide I formed, I am using 2 moles of methane, CH4. So these are going to cancel out. Times now I have the moles of the carbon monoxide. I can relate it to the molecules by using Avogadro's number. Always remember this relationship. Since I have the moles here, I know that for every 1 mole of the CO, because it's a molecule, right? So for every 1 mole of the CO, 1 mole of the CO, it contains 6.023 times 10 to the 23 molecules of the CO. So moles and moles are going to cancel out, and then you are going to end up getting your number in there. Every time you're asked about the number of molecules, then the number has to be a big number. Okay, this is going to be 22. This is going to be molecules of CO. It has to be a big number because you introduced the Avogadro's number. Another example, this is similar to number 32 in your homework. So oxygen can be prepared in the lab by heating potassium chlorate. So I'm starting with 2 moles of potassium chlorate and I'm heating this. This is a decomposition reaction, okay? So you start with one substance and decomposes into 2 substances in there. So potassium chlorate decomposes into potassium chloride and oxygen. I give you the equation, you need to balance the equations. You do not proceed with your calculations without making sure that the equation is balanced. The question is how many moles of oxygen could be obtained from 1 mole of the potassium chlorate. So you need the moles of oxygen. You can relate the moles of the oxygen to the moles of the chlorate, right? Potassium chlorate, because we know that for every 2 moles of the potassium chloride, you are making 3 moles of oxygen, right? So now let's go ahead and build the relationship in there. We need to cancel the moles of the potassium chloride. So I would say that for if I start with 1 mole of potassium chloride, because I want to cancel the moles of the potassium chloride, right? I want to do a relationship in there. So for every 2 moles of potassium chlorate, I am forming 3 moles of oxygen in there. So I can cancel those out, and then I'm going to end up having 1.5 moles of oxygen. This is similar to number 35 in your homework. In the reactions, this is similar again. It is a decomposition reaction where water decomposes into hydrogen and oxygen gases. I am starting with 2 moles of water. So I'm starting with 2 moles of water. And it says 2 moles of water will produce how many grams of oxygen? So if I'm starting with the moles of the water, I'm going to change the moles of the water to moles of oxygen. And then from the moles of the oxygen, I can change this into grams of oxygen. As simple as that. So I can simply relate the moles to the moles, right? Because it's in the same chemical equation. Relating the moles of the water to the moles of the oxygen. For every 2 moles of water used, I am making or I am producing 1 mole of oxygen, right? So we're going to go ahead and write that down. For every 2.0 moles of water, from where did I get the 2.0? It's the given. So it says like for every 2.0 moles of water in there, this 2.0 is not this 2 over here. It's given the number of moles of the water. So I want to change the moles of the water to the moles of the oxygen. Guys, no need to go into the grams of the water. No need. This is an additional step in there that you don't need because I start with the grams, moles, and then the grams of the other substance. Okay, so I bypassed the grams of the water. I don't need it. So I'm starting with the moles of the water, and I'm gonna do a mole ratio from the chemical equation. For every 1 mole of oxygen that is formed, I am reacting 2 moles of water. Okay, and I got this from here, from the balanced chemical equation. So you can cancel the moles of the water and the moles of the water out. And now I can change into the mass by simply using the molecular weight. So I need the mass, so the molecular weight has to be in the numerator for every 1 mole of oxygen. So the moles of oxygen and the moles of oxygen will cancel out, and this is going to be my answer.